Hey, thanks for joining me today. We're going to talk about factor patterns. For those who are following along with the curriculum, this is actually going to cover both 5.05 and 5.06. Factoring is tricky. There's just no easy way to say that. It's really tricky. And factoring at this level and what we're doing is we are coming up with just different strategies for factoring. Polynomials that can be factored, we're coming up with different strategies for recognizing when they can be factored and for factoring them. And there's a lot of vocabulary, and there's a lot of we're calling them patterns. There's a lot of patterns to be able to that we need to recognize. And so this kind of goes along with the whole idea of math is a language, a foreign language that we're trying to learn. And as you're trying to learn this language, it's really important that you get exposure to the language, so you're hearing people speak it. So one of my goals for this recording is that you're going to hear me speaking this language, and hopefully it starts to become familiar to you. You'll start to be able to recognize the nuances and the little differences between the words. Some of the words are going to be really close together, going to be really similar, so when you see them the first time, it's going to be like, didn't you just say that? It's the same thing. But then after repeated exposures, you begin to recognize the patterns and recognize the differences and the key points. So there are other recordings posted right next to this one that will walk you through similar factoring patterns, similar conversations about one or another of these. This is the recording that covers all of them. So this is the one that covers everything in one big, long recording. So hang on to your seats. But it's good to hear this a few times, or maybe to watch some of the other recordings. And definitely give yourself more than one chance to hear and interact with these factor patterns. Okay, so we're going to be able to factor polynomials using a whole bunch of strategies. We'll look at the greatest common factor strategy. We'll look at some formulas. I call them formulas. The book calls them patterns. There's 5 of them that we need to put on our notes. And then we'll look at trinomial factoring patterns and the way those work. And then we'll look at the last method, grouping. Okay, so jump right in. Factor by the GCF, finding the greatest common factor. What we're doing is we're going to look at our polynomial, in this case we have trinomials, and ask ourselves for each one, what number or monomial factor can be divided evenly into each, or what can be factored out. So here we have 3 terms, 3x to the 4th, negative 6x to the 3rd, and 15x squared, and we need to identify, well, what do they all have in common? And I hope that when you look at this, you can say, well, they all have an x squared in common. That's very true. They all have x squared in them. But they also all have a factor of 3 in them. And hopefully you can see that this is 3 times 1. And then the x to the 4th is really x squared times x squared. 6x cubed, that's negative 2 times 3, and then x cubed is x squared times x to the 1st power. And then 15 is 3 times 5, and then times the x squared. And so we can see that each one of these has a 3 as one of its factors. And each one of these has an x squared, at least one x squared, as its factor. Now that's the only thing they have in common. You can see that there's leftover, and each term has some factors left over, but those factors don't share anything in common with the other leftover factors in the other terms. So let's try that again. So what we do is we take out the factors that are common, the common factor, the greatest common factor, 3x squared, and then we put in parentheses all the factors that are left over. So the first term, 3x to the 4th power, we divide out the 3x squared. We're not subtracting, we're dividing. And we're left with 1x squared. left. And then that negative 6x cubed, we divide out the 3x squared, we're left with negative 2x. And the 15x squared, we divide out the 3x squared, we're left with positive 5. So we took out the greatest common factor, and that's one of our factors. It's actually 3 times x, so technically 3 factors. And then what's left over is a trinomial, still a trinomial, can't be simplified, you can't combine like terms. And it is x squared minus 2x plus 5. Now, it's possible that that trinomial itself can be factored again. Not in this case, but it could happen. So that's always something to watch out for. But that's our first method, factoring by the GCF. Why don't you hit pause and see if you could do it on the next problem. Same exact method. So when we're looking at our numbers there, one of the questions that arises is, how do you know what they have in common? And most of the time you can tell just by looking. But it sometimes happens that you need to write out the factors. What number can be divided evenly into 15? And of course we say 1 can, and not 2. 2 doesn't go in evenly, but 3 can. And not 4, but 5 can. Not 6, 7, 8, 9, nope, 15 can. So 3 times 5 is 15, so 1, 3, 5, 15. Those are the only factors of 15. 20, 1, of course, it's true for all of them. 2 times 10. 3, no. 4, yeah, 4 times 5, and so that means 5 is a factor, and then not 6 or anything with a 3. 2 times 10 was the 1, and then 20. So those are all the different numbers that can be divided evenly into 20. And number 10, that's 1, 2 times 5, 3, 4, 5, oh, no, just 5, and 10. So we wrote down all the factors of each one of these, and then we're just looking for what's the biggest one. What's the one that they all have in common? The biggest one that they all have in common. They all have 1 in common, of course, and they all have a 5 in common. So 5 is the greatest common factor. Now, that's one method for finding common factors. Whatever works for you to find the common numerical factor is what you should do. It helps me to write the factors down below, so I'm going to say 5 times 3, 5 times 4, and 5 times 2, just so I can get my number one. I can see the common number factors are all 5, but also I can see what's left over when I divide out the 5, what's left over. So I could do that mentally if I wanted to, but it helps me to write it down. So now notice that we can do the same thing with the x's. X cubed, x squared, the lowest number, the least number of x's on any of these terms is x squared. So that's going to be part of our common factor. So this first one has x squared times x, and then the second one has an x squared, and there's no other extraneous x's, and the third one has an x squared. And we'll do the same thing with the y's. Y squared, y cubed. So y squared is the lowest number of y's in any of these. So we document that. Y squared times y is y cubed. And the common factors are the x squared, the y squared, and the 5. So I'm circling those just to be really explicit, very clear with myself. Again, after a while you could probably do this without writing out the factors like I did there. You could probably do this mentally. But once we've identified our greatest common factor, the G is really important. It needs to be not just a common factor, but the greatest common factor, 5x squared, y squared. We divide those out, and then what's left in the first term is 3x, second term 4, and third term 2y. And again, if you couldn't combine like terms before we started, you can't combine like terms after we've factored out the greatest common factor. That's okay. It may be that trinomial that's left over could be factored some other way. Turns out not in this case, but it's possible. So always be keeping your eyes out for that. That's the greatest common factor. Now, the next page here is where you write down a bunch of notes. You can hit pause on the recording and do that. These are in your textbook on page 148. I'll just talk about them very briefly. The first one is the difference of squares. And it's just like what it says. It's a squared minus b squared, something squared minus something else squared. And if you can recognize that as a polynomial, as a binomial, if you have a binomial that is a subtraction, a binomial where you just have two things being subtracted, and both of them are perfect squares, then that's going to fit into this formula. Whatever that thing being squared was, and the first thing being squared plus the second thing being squared, and then the first thing minus the second thing. So a plus b times a minus b. Now, that brings up a really important point. For most of these patterns, it's going to be important that you are able to identify perfect squares. So we have that list. We've seen this before. 1, 4, 9, 16, 25, 60, 36. I was about to say the wrong number. 49, 64, 81. I hope you can recognize where these numbers are coming from. Do you know what the pattern is? And it can keep on going. We can keep on going. You can go as long as you want, but these are the primary ones. These are the ones you're going to see most often. Where did that pattern come from? Where did I get those numbers? Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. These are called the perfect squares, and it's an infinite list. It goes on forever, but more than likely you're not going to see any numbers bigger than these that you're going to need to recognize as perfect squares. And so when you're looking at a polynomial, if you see one of these numbers in that polynomial, then you recognize, oh, that's a perfect square, and then maybe that polynomial is going to fit into one of these patterns, which are all of them, or the first three anyway, based in perfect squares. The second pattern has something squared, again, a perfect square, plus 2ab plus another perfect square. So this time, instead of perfect square minus perfect square, we have perfect square plus another perfect square, and then in the middle we have whatever that thing being squared was in the beginning and the thing being squared at the end multiplied together times 2. We'll see in just a few minutes how that came about. But that factors out, the answer then is just that a plus b squared. We call that the square of a sum, and then there's the square of a difference with the exact same formula, the only difference being the minus sign here instead of a plus sign, produces a pair of factors, is a minus b times a minus b, with that minus sign instead of a plus sign. So a minus b squared is a minus b times a minus b. And again, we'll look at this in detail in just a minute. The last two factor patterns involve cubes. So it'd be good to write down a list of perfect cubes. 1 and then 2 cubed is 8, and then 3 cubed is 27, and 4 cubed is 64. That's the same as 8 squared. And then 5 cubed is 125. And we can keep on going if you want to, but those are probably the ones most likely that you'll see involving the perfect cubes. You have a difference of perfect cubes, and the sum of perfect cubes. Both are factorable and both have the exact same shape. The only difference is if it's a difference of perfect cubes, then that first term is a minus b. If it's a sum, it's a plus b. And then if it's minus in that first factor, then it's going to be plus in the second factor. A squared plus ab plus b squared. If it's plus in the first factor, then it's going to be minus in the second factor. A squared minus ab plus b squared. So those are the things you should have in your notes. Those are the formulas that you need to be able to recognize. So we'll see that here on the next page. Can you recognize any of these? Hopefully that first one, this is the most common, you'll recognize is a squared minus b squared. It's really easy to spot because it's the only binomial. Well, okay, I guess the a squared, a cubed minus b cubed is also a binomial. But it's the binomial, and when you see a binomial with a difference with a minus sign, this is what you should think of first, really. I mean, it's 9 times out of 10 is going to be this. It doesn't have to be, but it so often is. And so we need to check it out. Obviously, the first term is a perfect square, it's x squared. The second term, 16, well, that's one of the numbers on our list. This is x squared minus 4 squared. 16 is 4 squared. It's a perfect square. So we can put this in our formula. A plus b times a minus b. So that means this is going to be x plus 4 times x minus 4. And there it is. Now, it's really important when you're getting started using these patterns and doing factoring in general that you check your answers. Not just because sometimes the computer system has wrong answers in it, although that is the case, but also just so that you can see and get a feel for where this came from. So remember we talked about the FOIL method. We multiply the first terms together, that's the f, and then the outer terms together, that's the o, and then the inner terms together, that's the I, and then the last terms together, that's the L. So x times x is x squared, plus x times negative 4 is negative 4x, plus x 4 times x, the inner terms, is positive 4x, and then 4 times negative 4 is negative 16. And oftentimes when you do the FOIL method, most of the time, those middle two terms can be combined together. And this time, negative 4x plus 4x is 0. So you end up with x squared plus 0 minus 16. We don't write the 0. And that's what we started with. So remember that before we started factoring, we were doing this thing called multiplying. And when we multiply polynomials together, we use systems, procedures for multiplying. Multiply, we use the FOIL method. But now we are given the answer, x squared minus 16, and we're asked to come the other direction and come up with the question, what was the original question that gave us that answer, and that process is called factoring. So start with the factors and multiply them together, that's multiplying, and start with the answer and break it down into the factors, that's the factoring, that's called factoring, and that's what we're doing today. Okay, let's do the next one. Next one, 9x squared plus 30b plus 25. I hope you're already saying to yourself, hey look, perfect square, there's some perfect squares there. And there is the 9, which is 3 squared. And there's the 25, which is 5 squared. So notice that I took that 9n squared. Oh my goodness, and we've got a typo here. Let's fix that. I took that n squared and I turned it into 3. I took it and made it into a 3n, the whole thing squared. So that's 3n times 3n, which is 9n squared. So I just made it into one big sentence there. All right, we had the wrong variable going on there. Let's fix that one. Okay. Now, what formula does this make us think of? It's the one that has a square at the beginning and the square at the end, and it's a trinomial. I hope you remember off your list of factors, of formulas, that this one kind of looks like a squared plus 2ab plus b squared. Okay, now if this indeed is in that form, if this is that form, which, since this is an example problem, we're pretty sure it is, but we don't know ahead of time. We just know that the first term is a perfect square and the last term is a perfect square, so we need to do some figuring here. The square root of the first term is 3n, The square root of the last term is 25. If we multiply those together, 3n times 5, and then in the formula it says times 2. So 2 times 3 times n times 5. What is that? If that is the middle term, then we are good to go. This is the formula. And in fact, 2 times 3 times 5 is 30n. So we have our numbers, or we just showed our numbers to be fitting into the formula. So therefore our a is 3n, our b is 5, and the formula tells us that a squared plus 2ab plus b squared equals a plus b squared. So we can write that, we can just fill that in. Now we know a is 3n, b is 5, 3n plus 5 squared is our answer. Now, once again, we want to be sure we got the right answer, so we're going to check our work. We'll write this out to the side. 3n plus 5 squared, it means 3n plus 5 times 3n plus 5. And again, we'll use the FOIL method. 3n times 3n is 9n squared. That's our first term. 3n times 5 is 3 times 5, 15n. 5 times 3n, those are the inner terms, is positive 15n. And then the last terms, 5 times 5 is positive 25, which is what we wanted to be the last term. Middle two terms, again, can be combined. This time they're both positive. Add them together, we get 30n. So 9n squared plus 30n plus 25, which was the original problem. So we know that we're right. We know that this is, our factors are correct. We factored correctly. And they are 3n plus 5 times 3n plus 5, or 3n plus 5 squared. It's very important, because we're going to do the process both ways at first, as we're getting used to this, that we recognize what was the answer. The answer is the factors. The multiplying the factors together to get the original question is just the check to make sure that we got this right. Okay, let me show you this one. This one's not as commonly known. People don't always include these patterns, but it's kind of interesting, the difference in sum of cubes. So here we have a cube, n cubed, so that makes me think of a cubed plus b cubed. So let's see if that's what we have. N cubed, of course, plus, and then 125, that's on my list of perfect cubes, that's 5 cubed. So it fits the pattern. So what's the pattern? A cubed plus b cubed, off the notes, is a plus b times a squared minus ab plus b squared. So just plugging our a and b into the formula. A is n plus b is 5 times n squared minus 5n plus 5 squared, which is 25. And there we have it. There's the answer. Those are our factors. Because it fits the formula, we just plug it in. Now we can check this one also. This one's a little bit more complicated, right? N plus 5 times n squared minus 5n plus 25. So this is kind of a modified FOIL method. We're going to take the n and multiply it by each term. N times n squared is n cubed. N times negative 5n is negative 5n squared. N times 25 is positive 25n. And then we'll do the 5 times each of those terms. So 5 times n squared is 5n squared. 5 times negative 5n is negative 25n, and 5 times 25 is positive 125. Now I didn't have room to write all of those 6 terms, multiplications, on one line, so I wrote them on 2 lines, but I went ahead and lined up the common factors so that I'd have them all just right there nice and neat. So I have n cubed, a single n cubed, and then negative 5n squared plus 5n squared is 0. 25n minus 25n is 0. plus 125, and that's exactly what I wanted it to be. So that's not the answer. I shouldn't have put a box around that. That's just the check to see if we got the right answer, and we did, so we're good. Okay, just for fun, let's do this other one, and if you want to skip ahead in the recording, you can. This is kind of a goofy problem. I wanted to show you this one problem because it often happens that we can use more than one method, or in this case, more than one formula to factor. So we can factor, we can do factoring processes more than once. And this is an example of that. So n to the 6th power minus 64. Since we just did the sum of cubes, you might recognize this as a difference of cubes. Let's see if, before we do that, let's recognize it as a difference of squares. So that's what should first pop into our minds. N to the 6th power minus n to the 64th power, are those perfect squares? Well, the exponent on n is even, so we can write it as n to the 3rd power squared, so write it as a square. And 64 is on our list of perfect squares. It's 8 squared. So that fits into our formula. A squared minus b squared equals a plus b times a minus b. So we can write this as n cubed plus 8 times n cubed minus 8. All right, there we go. That was easy, right? But look at those factors. We have n cubed, that's a cube, and then 8, which is one of our perfect cubes, right? That's 2 cubed. That's n cubed plus 2 cubed. And we have a formula for that one. And then we have another one here. This is n cubed minus 2 cubed. And we have a formula for that as well. So we can factor each one of those. N cubed plus 2 cubed would be n plus 2 times n squared minus 2n plus 2 cubed, which is 4. And then n cubed minus 2 cubed would be n minus 2 times, and I'm going to have to go to the next line, n squared plus 2n plus 4. So we end up with 4 factors by applying the difference of square formula and the difference of cube formulas, and it would be interesting to see if we could have done the difference of cube formulas first and then the difference of square formulas. I think we could have, but I'll let you try that yourself. Okay, enough playing around. Let's go on to our next method. This is the simple factoring trinomials, kind of the simple trinomials. This is our trinomial that doesn't fit into any of the formulas. So x squared, that's a perfect square. Maybe this is going to work into one of our formulas. 12, oops, that's not a perfect square. Doesn't fit into our formula. But by now we should be pretty familiar with the idea that if you take two binomials and multiply them together, then they multiply together to be a trinomial. Okay, most times. Now, if there's terms that can't be combined, then it ends up being a 4-term polynomial, but most of the time we've dealt with binomials multiply together to produce a trinomial. So if this can be factored, then we would say there's no common factors, doesn't fit into a formula. At least there's a good chance it could be factored as 2 binomials. Now, remember when we're doing the foiling method, right? We've got our 2 binomials here, whatever they are. That first term times the first term, that's going to be the first term in our answer. That's the x squared. So that's pretty clear. Hopefully you all can see that x squared would be x times x. That's pretty easy. But then it gets a little more complicated. that first term times the last term, that's the outer terms, and then the inner terms, we get two different answers, right? If this is x, and then we have two numbers here, let's just say we'll call them a and b. So we have bx and then plus ax, those are our inner and outer terms. And those two are the ones that usually get added together, right? So whatever that middle number is, it's whatever the a and the b are added together. And then we do our last terms, that's a times b. So that last number, whatever it is going to be the two numbers that fit in those last two slots multiplied together. Now, that gives us a clue as to how this works. There is going to be in our binomials x plus some number here times x plus some other number there. And if you took the two numbers and multiplied them together, you would get our last number there, the 12. But if you added them together, you would get our middle number, the 7. So that gives us a clue as to how to think about the problem. Could we think of some numbers that multiply together to get 12 and add together to get 7? What would those numbers be? And the method that I want you to use is to be very systematic about it. You take the last term, 12, and you ask yourselves very systematically what multiplies together to get 12. We'll start with the easiest answer, 1 times 12. And then we'll go to the next easiest, 2 times what? 6. And then the next number down, 3. 3 times what? 4. And then we'll try 5. 5 doesn't work. Actually, we went around the corner here, right? 3, 4. And so we know we've come to the end. So those are all the different numbers, pairs that multiply together to get 12. And now we turn the question around and say, what happens if we add them together? 1 plus 12 is 13, 2 plus 6 is 8, and 3 plus 4 is 7. And there it is, 3 plus 4, 7. That gives us our middle number. So 3 times 4 is our last number. 3 plus 4 is our middle number. That must be the factors. And we'll multiply them out here. We'll try it. X plus 3 times x plus 4. X times x is x squared. X times 4 is 4x. 3 times 4 is 3x. And 3 times x is 3x, and 3 times 4 is 12. Combine the middle two terms, 4x plus 3x is 7x, gives us x squared plus 7x plus 12. And that's our original question. So that means that these factors are indeed the proper factors, the right factors that multiply together to give me that answer. Okay, there we have it. Piece of cake, right? Okay, let's try it one more time. Hit pause and you try this yourself on that second example there. This is one that you really should become very comfortable doing. You should be able to do this one yourself. And again, it's okay to just sit and watch me, but if you haven't done any of these problems yourself, then you haven't really helped yourself, like you haven't really learned it. So make sure that you're taking advantage of whatever opportunities you have to practice these problems yourself. All right, so we have that last term is 18. It's actually negative 18. Does that negative mess us up? Does that make us need to change our methods here? Turns out we can still do this. P times P is P squared. Those are our first terms. The factors of negative 18, the only thing that we have to remember is to get a negative, we have to have one of our factors be negative. So negative 1 times 18, that's the easiest one. Negative 2 times 9, negative 3 times 6, and then, let's see, 4 is not going to work, 5 doesn't work, so we're back to 6, but remember, one's positive, one's negative, so it's important to say negative 6 times 3, negative 9 times 2, and negative 18 times 1. Those are all the different ways to get a negative 18. One number is positive, one number is negative, and it matters which one's which. So we had to do all 6 versions. Now, remember, After we do that, then we come along and say, okay, which of these adds up to that middle number? You probably already know what the answer is, but let's do it methodically. Negative 1 plus 18 is 17. Negative 2 plus 9 is 7. Negative 3 plus 6 is 3. And that gives us a clue right there. Negative 6 plus 3 is negative 3. Negative 7, negative 17. So you can see that the one that adds up to the middle number, although technically we subtracted because one was positive, one was negative, but we added a negative number and a positive number, was the negative 3, was the negative 6 plus 3. So p minus 6 and p plus 3 are going to be the factors I'll use. And again, we can try these out. P minus 6 times p plus 3. We got to become really good at foiling as we go along. P squared plus 3p. Then the minus 6 times p is negative 6p. And then negative 6 times 3 is negative 18. Combine the middle two terms. 3p minus 6p is negative 3p. Minus the 18, put the p squared in front, and there we have it. So that's right. That means these factors work. I should mention as we're going along here that you're going to use factoring a lot. This is not just for this lesson or for this unit. We're going to use factoring a number of different times throughout your Algebra 2 course, so make sure that you're good at this. Don't take these skills lightly, because they really do come back to, don't want to be negative about this, they come back to haunt you. They come back a lot. And so if you get really good at this, it's going to make you very much more confident later on in future lessons. All right, this is our last method. This is the grouping method. I was never a big fan of the grouping method because it seemed to me that you had to really get the problem a problem in just the right shape, otherwise you can't use this method. But I just figured out that you can actually put any problem in this shape and it will work if it can be factored. You can factor using grouping. So I'll show you how to take a trinomial and put it into shape to be factored by grouping in just a minute, but let me show you just the grouping steps first. So if we have a 4-term polynomial, 2x squared minus 14x plus 6x minus 42, we're going to group the first two terms together. Go back to red here. And we're going to group the last two terms together. And then what we're going to do is we're going to just look at the first group, okay, 2x squared minus 14x. So we're going to go back to that GCF concept. What's the GCF of 2x squared minus 14x? So it's definitely a 2, right? 2 times 1 is 2, and 2 times 7 is 14. And then there's an x squared there, and there's a single x there, so it's going to be 2x. 2x is our GCF. Divide out 2x, and we get x minus 7. Okay, on our first term. Now in the first group of terms. The second group of terms, 6x minus 42, completely different GCF, right? Completely different. This is a 6 and an x, and this is 42, which, get my calculator out, 6 times 7 is 42. Right, so this has a common factor of 6, so put that plus sign down. 6, and then what's left over when we take out the 6x divided by 6 is x, and 42 divided by 6 is 7, and wouldn't you know it, both of the remaining terms after we take out the GCF were x minus 7. So x minus 7 times and x minus 7. So now we're going to kind of shift, this is kind of kooky. We're going to shift conceptually what we're thinking about. And we were thinking about these as two groups of two factors, and now I want you to think about it as one whole group of two factors. The two factors are 2x times x minus 7 and 6 times x minus 7. And what do those two groups have in common? Well, they both have an x minus 7. So if I take out the x minus 7, I divide that out from here and here, what's left over in the brackets is the 2x and plus 6. And there it is. There's my two binomial factors for this polynomial. This was written as a 4-term polynomial. It had 4 terms. But really it's a trinomial because you could combine the negative 14x and the 6x to be negative 8x. So we can check it. X minus 7 times 2x plus 6. We'll FOIL. X times 2x is 2x squared. X times 6 is positive 6x. Negative 7 times 2x is negative 14x. And negative 7 times 6 is negative 42. And there you can see we have all 4 terms, not necessarily in the same order. 2x squared, negative 14x, 6x, and negative 42. So it's this same exact problem. Again, we can combine the middle 2 terms, but we could have combined the middle 2 terms at the beginning. So it's the same polynomial. So what would we do? How would we figure this out if those middle 2 terms were already combined? How would we do that if it wasn't in the shape of 4 terms that we could then group into 2 sets of 2? Well, let me show you how to do that. This is cool. What we do is we take the first coefficient, first number, right? We have to have a squared, a variable squared, so we've got p squared there. And we take our last coefficient, the constant term, the number without a p, and we multiply them together. 3 times 24 is 72. And then we do that process we've been doing actually with the other method of taking 72 and just writing out its factors. 72 is 1 times 72, 2 times 36, 3 times 24, 4 times 18, 5, no, 5 doesn't work, 6 will work, 6 times 12. And we can stop when we get the pair of factors that add up to that middle number, which we have, 6 and 12. 6 plus 12 is 18. Okay, now, here's what we do. We're going to rewrite the problem, but we're going to split that middle term up into 2 terms. 3p squared plus, and then our 2 terms are going to be the 2 that add up to that middle term, 6 plus 12. So 6p plus 12p plus 24. Now, does the order matter? Turns out it doesn't. So if you want to, you could try this exact same problem, but change it around so it's 12p plus 6p, and you'll get the same answer. Let's see what we can do with this. Change my pen color and split these into 2 pairs of terms. Grouping, we're grouping them. So 3p squared plus 6p, the common factor is 3p. 3p times p equals 3p squared. 3p times 2 equals 6p. All right, and then the second group, 12p plus 24, I think you can see the common factor is 12. 12 times p is 12p, and 12 times 2 is 24. And there we have it, our p plus 2, common factors there, p plus 2. If we take those out, what's left over? 3p plus 12. And there we have it. We have our 2 factors. Notice that that 3p plus 12 could also be factored. And we could have taken out the GCF way at the beginning when we had 3p squared plus 18p plus 24, they were all divisible by 3. And this factor here is still divisible by 3. Divide by 3, divide by 3, we get p plus 4, and then times p. And so there's actually 3 factors, p plus 2, p plus 4, and 3. We could have divided out the greatest common factor here at the beginning, and then we would have had to only factor p squared plus 6p plus 8, and that would have been an easier problem to do. We wouldn't have had to do grouping, but you get the idea. There's more than one way to factor a polynomial in some cases, especially if there's more than 2 factors. Well, thank you so much for watching. I hope this was helpful, and don't let this be the first or last time. Don't let this be the last time you ever see factoring before you try to do this yourself on a test.